Topic 3, Lesson 4, Volcanoes and Earth's Surface, which can be found on pages 132 to 141 in your textbook. All right, as always, we're going to start with the connected. So to begin with, we need to circle and label the effects that the volcano in the photo is having on Earth's surface and atmosphere. So here at the circled spot, we have gases and ash are emitted, which you should do in your textbook as well. And then down here, we have lava flowing and hardening. Now that we've done that, let's list the effects that you identified in the photo and categorize them by the Earth system that is affected: hydrosphere, atmosphere, geosphere, biosphere. So, lava flows and hardens in hydrosphere and geosphere. Gases are emitted into the atmosphere, and lava flows kill organisms, which are, of course, in the biosphere. All right, volcanoes. A volcano is a structure that forms in Earth's crust when molten material or magma reaches Earth's surface. This can occur on land or on the ocean floor. Magma is a molten mixture of rock-forming substances, gases, and water from the mantle. Lava is magma once it reaches the surface. So few volcanoes are in the U.S. Where can we find these? And the majority of the volcanoes in the U.S. are going to be along the North American plate. All right, volcanoes and plate boundaries. At convergent boundaries, the subduction of an oceanic plate under a continental plate can produce volcanoes along the edge of the continent. At divergent boundaries, molten magma comes through the crust as lava, which quickly hardens into rock. But if the volume of magma is especially large, then a volcanic cone may form. So in Figure 2, divergent and convergent boundaries, we are supposed to describe what is happening on the left side of the diagram, where the ash is rising in the air over an active volcano. And in that, water in the subduction plate interacts with mantle rock to produce a plume of magma that is erupting at the surface of the overlying plates and building a volcano. At divergent boundaries, volcanoes form when the plates move apart and rocks rise to fill the space. Most of these volcanoes occur in the ocean. Since they occur in the ocean, most of these go unseen. So here we have an image, the dangers of submarine volcanoes. Gas bubbles lower water density and can cause ships to lose buoyancy and sink. So we have the volcano, which is degassing, causing those gas bubbles to form, which can cause ships to sink. At convergent boundaries. In the process of subduction, trapped water leaves the sinking plate and mixes with the material of the overlying mantle, causing it to melt. Magma rises, and if the magma reaches the surface before cooling, a volcano forms. If this is part of the ocean floor, the resulting volcano begins to form on the seafloor as a seamount. It may eventually become a volcanic island. Hotspot volcanism. So a hotspot is an area where lava frequently erupts at the surface, independent of plate boundary processes. Most hotspots sit atop mantle plumes of hot rock. As a plate moves over the plume, a chain of volcanoes is created because the older volcanoes keep being carried away from the hotspot. So here we have this modelet, the hotspot modeling. The Hawaiian Islands have formed from the movement of the Pacific plate over a hotspot plume. Using the diagram as inspiration, design a functioning physical model of how a hotspot makes volcanoes on the ocean crust of a moving plate. Sketch or describe your model in the space here. Include details on how it would work. So go ahead and do that in your textbook. Also, we're going to go ahead and do the reading check. The Aleutian Islands of Alaska occur in a chain near a plate boundary. What type of boundary is it? And it's going to be a convergent boundary. Volcano landforms. Magma usually forms in the layer of hot rock in the upper mantle. Because magma is less dense than the rock around it, it cracks on its way up to the surface. Once the magma exits a volcano and is exposed to air or water, it is then called lava. Volcano parts. Inside a volcano is a system of passageways through which magma travels. Below the volcano is a magma chamber. Magma moves up from the chamber through a pipe, which leads to the central vent, opening at the top, which may be in a bowl-shaped crater. Some volcanoes have side vents too. Bombs are large chunks of hardened lava. Cinders are the size of pebbles. The finest particles are called ash. Volcano parts. Composite volcano. So figure 4 is a composite volcano which has alternating layers of hardened lava and ash. We're going to complete the diagram by reading the description of the volcano's parts and writing in the missing labels. So here to the left we have the pipe, which is what brings the lava up. Underneath we have the magma chamber, where the magma is stored before going up the pipe. And finally we have the side vents, which are, of course, the side areas where lava or magma escapes the volcano and becomes lava as it interacts with air. Okay, volcano types. The volcano in figure 4 is a composite volcano, also called a stratovolcano. It is made of alternating layers of lava flows and ash falls. These tend to be cone-shaped and tall. Mount Fuji in Japan is an example of a composite volcano. Other types of volcanic formations are shown in figure 5. So while we're looking at these, we need to think about how shield volcanoes and lava plateaus are similar and how they're different. All right, on the left-hand side, we have our shield volcano. So some volcanoes have slow, steady eruptions in which lava flows out and builds up over a broad area. Hotspot volcanoes tend to be shield volcanoes, and they can be massive. Lava plateaus are where lava can flow out of several long cracks in Earth's crust and flood an area repeatedly over many years. Over time, these relatively flat layers of hardened lava build up into a lava plateau. All right, and back to our figure 5. How are shield volcanoes and lava plateaus similar, and how are they different? Both are volcanic formations which cover large areas. A lava plateau is flatter, though, than a shield volcano. Okay, the two other volcano types we have are the caldera. A caldera forms when a volcano collapses on itself. We also have cinder cone volcanoes. If lava emerges from a new vent in Earth's crust as a mix of bombs, ash, and cinders, these materials build up into a cinder cone volcano. The loose, ashy material tends to erode quickly. So along with our last question of how are shield volcanoes and lava plateaus similar and how are they different, we're also supposed to review the 3 steps of the caldera formation and finish the sentence to describe the second phase of the caldera formation. So, again, the caldera forms when a volcano collapses on itself. So large eruptions empty the main vent and magma chamber of the volcano. Lacking support, the top of the volcano collapses inwards, and then a lake fills the caldera. Later eruptions form a small cone. Volcano hazards. Extinct volcano, or dead volcano, is a volcano that poses very little threat of erupting. A dormant volcano is like a sleeping volcano. It poses little threat, but it could reawaken someday. And then an active volcano are the more immediate threat. Volcanologists classify eruptions as quiet or explosive. Quiet eruptions. If the magma in a volcano's magma chamber is hot or low in silica, it will erupt quietly. The lava will be thin and runny, and trapped gases will bubble out gently. The Hawaiian Islands continue to be produced mostly by quiet eruptions. And comparatively, we have explosive eruptions. Magma that has a lot of silica will erupt more. High silica magma is thick and sticky. It causes a lot to build up in a pipe until pressure is so great that it bursts out over the surface. Trapped gases explode out instead of bubbling out gently. These can hurl lava, ash, cinders, and bombs high into the atmosphere. So you can think of this kind of like a balloon. If we blow up a balloon and we keep blowing it up until it's past its capacity, what happens? It explodes, basically. It pops. It makes a loud noise, and then pieces go everywhere. And that's basically the same thing that's happening with our volcano in an explosive eruption. Math Toolbox, magma composition. So here we have two types of magma. We have low silica and high silica. So magma is classified according to the amount of silica it contains. The less silica the magma contains, the more easily it flows. More silica makes magma stickier and thicker. Trapped gases can't emerge easily, so eruptions are explosive. Okay, so our low silica has about 50% silica, whereas the high silica magma is comprised of about 70%. So we're going to use the information we have from here to answer the following questions. How do the two magma types compare in terms of silica content? And the high silica magma has 1.4 times the amount of silica. 50% times 1.4 equals 70%. So in order to find that, we would have divided 70 by the 50, gotten 1.4. Then, which of the magma types would erupt more explosively? How would knowing the type of magma a volcano produces help nearby communities prepare for eruptions? So high silica magma would be more explosive because it doesn't flow as easily or allow gases to bubble out as readily. If an active volcano were known to have high silica magma, evacuation should be more widespread because bombs, cinders, and ash could be thrown far. Predicting volcano hazards. Volcanologists use different tools to monitor volcanoes and predict eruptions. Gas emissions are monitored, chamber swelling is measured, and volcano tilt is monitored to help predict eruptions. They can notify the public of possible predictions. So let's go ahead and do our reading check. If the concentration of sulfur dioxide emitted from a volcano increases from less than 1 part per million to 4 parts per million, is that volcano more or less likely to erupt? And our answer is going to be that it is more likely. An increase in sulfur dioxide concentration is associated with increasing activity and elevated risk of eruption. Question it. So building on a volcano. In some parts of the world, building on a volcano is a necessity because most of the land is volcanic. Suppose you had to build a home on a volcanic island. What questions would you want to answer before choosing a specific site for construction? I want you to go ahead and answer what these questions are, and then when you're done with your workbook, bring that to me. And I'll tell you what I want to do with that information afterwards. So that ends lesson 4, and now it's time to do the lesson 4 check. So 1, running lava oozes from the vent of a broad, gently sloping shield volcano. What type of eruption is this? And that would be a quiet eruption. 2, why do volcanoes form at divergent and convergent boundaries? In order for a volcano to form, magma from inside Earth must be able to reach the surface. This can usually happen at divergent boundaries, like mid-ocean ridges, or at convergent boundaries, like subduction zones. 3. The Hawaiian Islands, formed as the Pacific Plate has moved west-northwest over a hotspot. In which part of the islands would you expect to find the most active volcanoes? What about dormant and extinct volcanoes? Explain. The active volcanoes would be in the east-southeast end of the chain. The dormant and extinct volcanoes would be in the west-northwest end. The plate is moving west-northwest, so the age and inactivity of the volcanoes would be greater in that direction. 4. You are sailing in the South Pacific Ocean, far from any plate boundary. Looming on the horizon is a dark, broad, rounded island with sparse vegetation. A few thin flows of orange lava drip into the sea. Some smoky vapor unfurls from the center of the island. What kind of volcano is this? Explain. Most likely, it's a shield volcano, or a hotspot volcano, based on the shape, size, and slow eruption, and its distance from any plate boundary. 5. How are volcanic island arcs formed? Subduction of oceanic crust results in plumes of magma rising up through the overlying plate. If the magma penetrates the crust, it can form volcanoes that may grow tall enough to become islands. A series of these may form along the plate edge in a row or arc. And that concludes Lesson 4.